Hi, this is Tzvi Rosen. Welcome to the first lecture in our History of Calculus course. In today's lecture, we're going to talk about what we mean when we say calculus, so we know what we're looking for as we approach the history. And then we're going to go back to ancient Greece and talk about the paradoxes of Zeno of Elea. As just a first disclaimer, I'm not a historian, so please forgive me in any lapses in historical standards, but this is meant more as a mathematical exercise, understanding where these mathematical ideas came from originally to enrich our understanding. Okay, thank you for joining me. So we'll start discussing, as I mentioned, what is calculus. First, we have limits. Using limits, we can define derivatives. You can also use limits to define some important transcendental numbers. So here you can think about e and pi, and any real number, for that matter, a complex number, which doesn't satisfy a polynomial equation. Then we can talk about infinite series, and these can also be defined in terms of limits, but these are sums of infinitely many numbers. And using infinite series, we can define integrals, which are areas that can be defined by a limit of a sum of infinitesimal areas within a region. When we talk about limits, there are two contexts where we're usually talking about them. So either in the context of sequences, and here we're talking about some list of numbers, an, where n takes values 1, 2, 3, etc. And when we say that the limit as n approaches infinity of an equals L, then what we mean is an gets arbitrarily close to L. Okay, so meaning by arbitrarily close, we mean as close as we want it to get. And let's give a rigorous formulation of that. So what this means is for any epsilon greater than 0, there exists some large index n such that for any other index past n, the size of a sub n minus L will be bounded above by epsilon. Okay, that's what it means for the limit of an to be L. Okay, we can also talk about limits in the context of functions. So if we have f of x, a real valued function on the real numbers, when we talk about limit as x approaches x naught of f of x equals L, what that means is that if x is sufficiently close to x naught, f of x gets arbitrarily close to L. Okay, and if we want to formulate this in a rigorous manner, we'll say that for any epsilon greater than 0, there exists a delta greater than 0, such that as long as your input x is within delta of x naught, then this implies the value of the function will be within epsilon of L. Okay? And this is the delta epsilon definition of a limit that's feared by calculus students everywhere, but this really didn't develop until very late in the history of calculus. Okay? This rigorous definition. So our intuition should just be that when we're close to some fixed value, the function values get closer and closer to whatever limit we're thinking about. Okay. Now we can talk about derivative, and this is a topic that the inventors of the calculus were really interested in. It's one of the key operations in calculus, and it's defined using a limit. So let's say we have f of x, a function. Okay, and here we'll take a graph of some function. Okay. We might be curious about the tangent to the curve at various points. Okay, and we'll take this to represent the instantaneous rate of change, or the instantaneous slope of the curve. Okay. So the derivative is the instantaneous rate of change of f of x. Okay? And in particular, if you're interested in the value of this derivative at a point x naught, let's say, that'll be the rate of change of f of x at x naught. Okay? And this is defined in terms of a limit. It's defined as the limit as h approaches 0 of f of x plus h minus f of x divided by h. And the idea here is that, okay, looking at one particular curve, okay, let's say I want to understand the derivative at this point. One way to do that is to take secants to the curve getting closer, where the second point gets closer and closer to the initial point. Okay, and once that point approaches our initial point all the way, well, then the fraction will cease to be defined, because then you have on h on the bottom, which is 0, and f of x minus f of x, which is also 0. But assuming that the secants approach the tangent, this will be a well-defined limit which defines the slope. Okay, now we can talk a little bit about transcendental numbers, and this won't be the real focus of the course, but it is something that comes up periodically. And we say that a number is algebraic. So a number is algebraic over Q. Okay, sometimes over Q is omitted because this is what people mean when they say algebraic. If it is the solution to a polynomial equation with integer coefficients. Okay, an example of this would be any rational number this is the solution to the equation qx minus p equals 0. Okay? So if a number is not, but obviously it's more than the rational numbers that are algebraic, any square root, any cube root, any solution to an equation, which does not just include radicals, but yeah. So if a number is not algebraic, it's called transcendental. This is a property which is very hard to prove, because proving that no polynomial equation will be satisfied by whatever number you're looking at, that's a very bold statement to make. It means you can be confident about the values of all polynomials evaluated on this number, that they don't give you 0. That's a lot to prove. However, there are tools to do that, and we'll hopefully touch on those later in the semester. But there are some very important numbers that are defined in terms of limits that are transcendental. So one of them is the limit as n approaches infinity of 1 plus 1 over n to the n. This is known as E, and this is approximately 2.718281828, followed by other stuff. It repeats that 1828 twice, so you get a lot of precision if you remember those 4 digits. So being able to define that limit means that E is something that kind of has to come out of the calculus. Okay, well, we can also talk about infinite series. So a sequence was a list of terms, A1, A2, etc. But we can talk about a series, n goes from 1 to infinity, of an. This is the sum of all of these terms. And you would object, how can we do that? We can't add infinitely many numbers. Addition is something you define between 2 numbers, and then inductively any finite collection of numbers. But we can't add infinitely many numbers. And the response to that is, you're right, we're going to define this in terms of a limit. So first we'll define a partial sum. This will be the sum of the numbers a1 plus a2, etc., up to an, okay, where n is some index. Then we can define this sum as the limit as n goes to infinity of Sn. Okay? And just a quick couple of examples of that. The sum of 1 over 2 to the n is known to be 1. Okay, and there's various ways to derive that. And the sum of 1 over n, where n goes from 1 to infinity, is infinity, meaning it diverges. In other words, the partial sums will grow without bound. Okay. And the final thing on our list of calculus concepts to be keeping an eye out for is integrals. And integrals are written as follows. So if you have f of x, a real valued function, then the integral from a to b of f of x dx, this defines the signed area of, or between the graph of f of x and the x-axis between, or on the interval a to b. Okay, and just a cartoon to know what we're talking about. If we have this function, okay, then the area below the x-axis will be added with a negative sign. The area above the x-axis will be added with a positive sign. Okay, and this is a to b. Okay. And so how do we understand this as a summation? Okay, I mentioned before that integrals can be thought of in terms of infinite series, and they can because we can talk about, so let's take this picture, and instead of taking the true area, we can, we can take the rectangles that look like this. Okay, so we're splitting this up into small negative and positive rectangles. And then we add up those rectangles, and that's an approximation for the integral. Okay? But obviously, it won't be the precise answer, so we want to take a limit as those rectangles get smaller and smaller, which leads to an infinite sum. Okay, so we take the limit of the sum of rectangles as they get smaller and smaller. Okay, so obviously I didn't give any of this a particularly full treatment. I'm just trying to refresh your memories from your calculus course so that as we talk about ideas coming up in ancient Greece and then later throughout history, we can see how they connect to what we know about the calculus. Okay, so thanks for your patience with that introduction. And now let's get to Greece. We're starting with Zeno of Elea. And he lived approximately 490 before the Common Era to 430 before the Common Era. He was a Greek philosopher, and he lived in southern Italy. That's where Elea is. He was a student of Parmenides, and there's a myth that there was a tyrant who ruled Elea, and he asked to, and he encountered Zeno, and Zeno said that he needed to whisper some secret to him. And when the tyrant drew close, Zeno bit down on him, and he only released his bite when he was stabbed to death. So that's a colorful tale about Zeno of Elea, but we know about him as an author of paradoxes. Traditionally, Zeno authored 40 paradoxes, but only 10 of them survive in the writing of other Greek philosophers, particularly Aristotle. When we say paradox in this context, we're talking about a sequence of logical steps that arrive at a contradiction without a clear resolution. Okay, there's no obvious way to say, here's where your reasoning fails, and that's why you arrived at a contradiction. So we're going to consider 4 of Zeno's 10 surviving paradoxes, and they are the dichotomy paradox, the Achilles paradox, the arrow paradox, and what we'll call the infinite divisibility paradox, though it's less universally known as that. Sometimes it's called the paradox of parts and wholes. Okay, we'll start with the dichotomy paradox. So Zeno's arguments about, this is a quote from Aristotle, Zeno's arguments about motion, which cause so much disquietude to those who try to solve the problems that they present, are 4 in number. The first asserts that the non-existence of motion on the ground that that which is in locomotion must arrive at the halfway stage before it arrives at the goal. Okay, so what's the idea here? So the idea here is, let's say you're over here, and you want to arrive at a finish line. Okay, so there is a list of things you have to do before you get to that finish line. In particular, you have to get halfway, and before you get halfway there, you need to get halfway to that halfway mark, so the 1/4 mark. And before you can get there, you have to get to the 1/8 mark, which is halfway to the 1/4 mark. And before that, you have to get to the 1/16 mark, etc., etc., etc. Okay, you're going to get arbitrarily many halfway marks, infinitely many halfway marks. So that means we have an infinite list of places to reach before we get anywhere. Okay, that's the dichotomy paradox. Okay, so you can't get to that finish line because there's too many things to do first. You have to go to too many places first. Okay, now we talk about the Achilles paradox. The second, this is a quote from Aristotle in the same place. The second is the so-called Achilles, and it amounts to this, that in a race, the quickest runner can never overtake the slowest, since the pursuer must first reach the point whence the pursued started, so that the slower must always hold the lead. This is kind of a similar notion to the dichotomy paradox. So here's a cartoon of Achilles and a tortoise racing a tortoise. So obviously, a tortoise is very slow, and Achilles, the great hero of the Trojan War, is very fast. But in order to get anywhere, so Achilles first has to get to where this tortoise first was. So he'll get there. Okay, and that's what happens here. He ends up where the tortoise just was, but then the tortoise has already moved, okay, some small amount. Okay? So the tortoise has moved, so now Achilles has to get to that point. Okay? But then the tortoise will move again. Okay, not a lot, certainly not as much as Achilles moved, but he'll still move to a new point as long as the speed of the tortoise is positive. So continuing this on indefinitely, this means Achilles will never catch the tortoise. Okay, so why is this a paradox? Because we can see with our own eyes that Achilles must catch the tortoise. Like Achilles will obviously outstrip the tortoise in short order. Okay. Now we can look at the arrow paradox. Okay, and this is from a different paragraph, but close by in the same book of Aristotle. If everything, when it occupies an equal space, is at rest, and if that which is in locomotion is always occupying such a space at any moment, the flying arrow is therefore motionless. Okay, so the idea here, it's a little difficult to translate into, let me see if I can get an arrow. Here we go. Okay, so let's say we have this arrow. Add some feathers. Okay. So, okay, we shot this arrow out of a bow, and it's going to go some distance. Okay. So, how would we tell how fast the arrow goes? Well, we'd measure the distance that it's going, and we'd time how long it takes to get there. So the speed will be the distance over time. Okay. Well, that's great, but let's say we want to get a very fine, we know that the speed of the arrow might change over time, so let's say we want to get a really close estimate for the speed of the arrow. So what we could do is take a shorter window. Okay, so let's get a shorter window on this arrow. So we'll measure this shorter distance, and then we'll divide it by the time it takes to go that shorter distance to get a really fine view of what that speed is. Okay, now here comes the paradox. What if we just measure it, we shrink that interval all the way to a point? So we want to get the finest reading on its speed. Well, at that point, there's no distance at all. So the distance equals 0, so that must mean the speed equals 0, right? So distance equals 0. Okay, so questionably, we assume that implies that the speed equals 0. Right? You need to travel some distance in order to have a speed. So if at the given point where we're measuring its speed, it's going 0, and the same would be true wherever we measured it, right? Because as long as you zoom down far enough, the distance that it travels is 0. So its speed must be 0. That tells us that the arrow must never move. That the arrow always has speed 0. Okay, that's the arrow paradox. And finally, an example of a paradox not related to motion, and we're taking this from a different spot in Aristotle. Here he doesn't attribute it to Zeno, but Simplicius attributes it to Zeno in another place. And it goes as follows. To suppose that a body is divisible through and through, and that this division is possible involves a difficulty. What then will remain? A magnitude? No, that is impossible, since then there will be something not divided. Whereas, ex hypothesis, the body was divisible through and through. But if it be admitted that neither a body nor a magnitude will remain, and yet division is to take place, the constituents of the body will either be points or absolutely nothing. If its constituents are nothings, then it might be both come to be out of nothings and exist as a composite of nothings, and thus presumably the whole body will be nothing but an appearance. But if it consists of points, it will not possess any magnitude. Okay, so the idea here is we have this idea that stuff exists. Okay, so let's say it's a rock, let's say it's something with matter with stuff. Okay, well we can divide it, and then we can divide it again. Then we can divide all of those pieces. Then we can divide all of those pieces. And you keep doing that as long as any piece, any piece is bigger than 0. Has any kind of positive mass, you can keep splitting it up. And if you repeat this, repeat until all parts are of 0 magnitude. Well then, if any part has 0 magnitude, and this kind of thematically is similar to the arrow, if all parts are 0, that means that the whole is 0, right? And that's a paradox, because we know that the whole thing started out with some stuff. Okay, so here were 4 paradoxes attributed to Zeno, and all of them kind of involve breaking something down in some kind of infinite process and arriving at a contradiction. So let's dive into where Zeno's error is. Well, in the dichotomy paradox, Zeno makes the assumption that it takes an infinite amount of time to reach an infinite number of places. So if you have infinitely many halfway points, that means you would require infinitely much time to visit all of them. In the Achilles paradox, it's similar to the dichotomy paradox, just the finish line moves. If the tortoise occupies infinitely many places, Zeno assumes that means it would take an infinite amount of time to follow the tortoise in those places. The arrow paradox, Zeno assumes that when considering an arrow in one place, its velocity must be 0. Okay, when that's, as we'll see, that's not an assumption we have to make. And in the infinite divisibility paradox, we're saying that a size can be given to all parts, including infinitesimal ones. So Zeno says it must be that all of these tiny parts have size 0, and so putting them together will get us something of size 0. And we can see that Zeno is anticipating the importance of calculus in these paradoxes. In the dichotomy paradox, you can answer this by saying that the real numbers are a continuum, and you can have infinitely many numbers living in a finite interval. So you can proceed through that finite interval, occupying infinitely many positions, but going through it in a finite time. So too with the Achilles paradox. Achilles overtakes the tortoise because he can occupy infinitely many places in a finite amount of time. The arrow paradox, that can be solved using the derivative. The velocity is the time derivative of displacement, which is a limit as time goes to 0. So Zeno thought that because the distance at in a moment is equal to 0, that means that the velocity must be 0. But we know through the definition of a derivative that both the distance and the time taken to travel that distance are approaching 0, so their ratio may approach some non-zero limit. As for the infinite divisibility paradox, we can think about this as related to infinite sums or integrals. You can have a limit of some sum where all of the constituents are approaching 0 size, and yet the sum approaches some finite value. Okay? So I really liked learning about Zeno's paradoxes. I think it emphasizes some important themes going forward in the class. We're going to be talking about limits at infinity. We're going to be talking about limits as small quantities approach 0. We're going to be talking about infinite sums of infinitesimals. And most importantly, a theme that we're going to see is the necessity of rigor in our mathematics to avoid the absurd, as Zeno was forced to confront it. Thank you so much, and I'll see you next lecture.